Good afternoon, class. So, happy Chinese New Year to all of you. Okay, today we will cover tutorial 3, which is the makeup for this week. Okay, before we start, let me briefly go through some of the important methods that we have learned in the first 2 weeks. Right, I basically posted this materials in the course website. You should go through it because it basically let you understand all the methods, right, in a simpler way by using a very simple circuit. So the purpose is to get familiar with the methods, right? And basically I have gone through all this as well during some of the past tutorials, and we use this simple circuits in question 1.1, first tutorial, first question, part A, for several systems circuit analysis methods. Right? Firstly, node analysis is that you assign node voltages. Okay, if it's known, just put the node voltage there and only solve for the unknown. And here we have only one node voltage, which is V. And by looking at the current entering and leaving the nodes with the unknown node voltage, you can write down an equation. Okay, you have only one unknown, so one equation is sufficient. Okay, which gives us this equations. 12 minus V divided by 4 is the current entering through the 4 ohms resistor, and we have current leaving through the 6 ohm and 3 ohm resistors, right? Because the other end is connected to a known reference node as well, which is 0 volts. And from here we can easily solve the equations. Okay, you can also use mesh analysis to do it. Okay, when you assign mesh current this way, right, take note that it means that this is current I1, while this is current I2. So I2 is equal to Ix, right, which is what we want to solve over here. Okay, unlike this nodal analysis, which we have only one node voltage, in this case you have two mesh currents. So basically the number of knowns may give you a suggestion on which method to use, right? So before you jump into solving it, you may want to take a note of that. Okay, when the method is not specified. If the method is specified, then you have to use, right, the particular methods which is stated. So here, if you apply Kirchhoff voltage law around the loop, right, going around the loop 1, you can write down one equation. Then you go around mesh 2, you write down another equations. So the whole idea is to express this equation in terms of the mesh current, okay, which is what you want to solve. So solving two equations with two unknowns, you can easily get I2, which is your Ix. So this is using mesh analysis, and we can also use source transformations to transform this voltage source, right, in series with resistors to a current source which is in parallel with a resistors. Now, source transformation is useful in simplifying circuits because in some cases, right, you cannot simplify just by combining the resistor because there's a source there. Right? In this case, you should use source transformations. For example, over here, you can see that these two cannot be combined. Right? If you want to simplify it from the left-hand side, and we can use source transformations to transform it to a current source in parallel with a resistors. Now, because the 6 ohm is now in parallel with 4 ohms, actually you can start simplifying from the left-hand side. Okay, but in this case, if you just want to find what is Ix, you can directly apply current division law. The current flowing through the 3 ohm resistors, Ix, is portions of 3 amperes, right, according to the ratio of the conductance, right, 1/3 divided by the total conductance, 1/3 plus 1/6 plus 1/4. And by this, you can see that you can get the same answer for Ix. Okay, lastly, Thevenin's theorems is another way of simplifying the circuits. And this involves finding two variables, the Thevenin's voltage, which is represented by an independent voltage source, and the Thevenin's equivalent resistance, right, which is in series with this voltage source. So similarly, you can see that you can transform it to Norton's. Okay, once you get Thevenin's, you can also transform it to Norton's equivalent. And to find VTH, you must first remove the load, take out this load, and you have open terminal. The voltage at the open terminal is your VTH. And to find this VTH, which is the open circuit voltage, you use any method that you have learned. I've just gone through them. You need to select one of them. Okay, which method to select, as I mentioned, it depends on the variable sometimes. Okay, and in some cases, if you can just simplify it by series parallel, just go ahead. If not, then use nodal or mesh analysis, depending on the number of variables. Right. So this is for VTH. To find RTH, you need to kill all the independent source, right? All the independent source. And then find the equivalent resistance, okay, which means that after you remove all the sources by making them equal to 0, okay, then look into this terminal, what is the equivalent resistance, right? And that will be your RTH. Okay, and for this circuits, right, take note that we can find RTH by simply killing the independent source. Right, this is V equal to 0. Right, I go back to this one. If I put this equal to 0, V equal to 0, right, and then open this terminals. Okay, I'll get the circuit something like that, and that means that you have 4 ohm in parallel with 6 ohm, right? 4 ohm in parallel with 6 ohm, which is 2.4 ohms. Okay, where the load resistance 3 ohm has been removed. Okay, and another way to determine RTH is actually by injecting a known source. Can be a voltage source or a current source, right? As I mentioned. For this method, this is useful if there's a dependent source or control source. Okay, but it can also be used for circuits without dependent source. So this method is general. But however, if there's no independent source, you can see that there's only resistors, pure resistors, and you can simplify them easily by series parallel star delta, right? So you need not use this method, but it can be used as well, right? Especially in cases where you're not sure whether they are series or parallel. Okay, if I pump in a known voltage source, the purpose is to calculate this current. Then resistance, according to Ohm's law, is voltage, 1 volt, right, divided by current, which is what you need to determine. Now, how do you determine the current? Use any method that we learned in week 1 and week 2. For example, just in this case, use Kirchhoff current law at this node. Why? Because 1 volt is applied across 6 ohm as well as 4 ohms, right? This is connected to ground. So 1 divided by 6 is the current flowing through here. 1 divided by 4 is the current flowing through here. You add them up, you get a total current flowing into the terminal, right, which is equal to outflow. And 1 over I, it means 1 over this value, is also equal to 2.4 ohms, okay, which is exactly the same as this. So this method is easier. You can see that you just straight away do it. Well, this method is more complicated, but you get the same answers. It is useful if there's a dependent source, right? There's dependent source. Okay, after that, you can put back your load. Put back your load to the equivalent circuits. Okay, because we have simplified everything on the left to this equivalent circuits. Okay, this is useful if you need to change this quite frequently. For example, now if I say that I analyze the current I for 5 ohms, 10 ohms, 100 ohms, you can see that I need not do it 3 times again, right? I just replace this by whatever value I have over here. I can easily find my IX. So this method is useful if the load is changing frequently, and it is also useful to calculate the maximum power, right? Once you see the maximum power, then you can just straight away use Thevenin's equivalent. Now, maximum power is drawn when this load resistance is equal to the Thevenin's resistance. Okay, which means that you should change your load to 2.4 ohms, then maximum power, right, will be delivered to this load. So this is basically what we have learned for the circuit analysis method, and we also learned about op-amp. Okay, for op-amp, as I said, just remember this condition only, right? Only these conditions, which is V plus is equal to V minus. Okay, the voltage at the negative terminal must be equal to the voltage at the positive terminal. Okay, this means that if one of them is known, you know the other as well, right? And the other point is that I plus is equal to I minus, meaning that no current can enter this branch because of the infinite resistance. So basically only these two conditions. Okay, after you impose these two conditions, you can see that you're just assigning some known voltage and known current, right, at certain part of your circuits. You can treat it as if the op-amp is not there by just looking at the node voltage, right, as well as the branch current. So this is what we have done in week 1 and week 2. Okay, for this week tutorial, you start to learn about energy storage elements. Okay, most of you would have problem for this part because of the differential equation. So I suggest that you should review some of the max in differential equation, right? And then after that, it will be easier for you to understand. So the main problem is the max, I would say, rather than the circuit theorems. Okay, let us look at a resistor circuit resistors component first, which we have done many times in the past 2 tutorials. Ohm's law, V equal to IR. Right? You can interpret this equation this way. Given I, you use IR to find V. Okay, we can also put this equation this way. I is equal to V over R. It means what? Given voltage, divide by R, you can find I. Right? So this one has no problem, but actually you can also interpret the capacitor's equations in a similar way. I is equal to C dV dt, must remember it. I is equal to C dV dt. All the properties of the capacitors is from this equation. Right? So you must remember it like you remember Ohm's law. I is equal to C dV dt. What this means is that given the voltage, you differentiate it with respect to time. Right? Differentiation comes in. Multiply by C, you get I. Ohm's law is direct. I multiplied by R, you get V, right? V divided by R, you get I. But this one involves differentiations. If you have a voltage of across a capacitor, you differentiate it, multiply by C, you get I. Okay, and you use the passive sign conventions. Current flow from higher potential to lower potential, right? Passive components. Current always flow from high to low. So in this case, right, for capacitor, we also say that it is charging. It's charging, it is absorbing energy. And if you integrate these equations, right, the reverse of differentiation is integration. If you integrate this equation, you get this V is equal to integrations of I divided by C plus the initial voltage. Now this equation is quite easy to understand. Now suppose that your handphone, right, is 20% left, right? It means that there will be a signals indicating that there's 20% left, and then you start charging. This means that there's an initial voltage. What is additional will be from the current, which is passing through it. Then you will start charging up, right? So when the current is flowing inwards, it's a passive component. This is charging up. Okay, when the current flow the other way around is against the potential difference from low to high, is discharging. Okay, which means that For example, you fully charge out your handphone, you remove it from the power source. Now your battery is supplying power, right? It's supplying power, so current flow the other way around. Now in this case, you should put I equal to negative, right? So if I inflow, you put positive, I outflow, you put negative. And this equations over here, right, is actually given I. Given the current flowing in or out, you integrate it, divide by C, right? You get the voltage add on top to these capacitors. And adding it up with the initial voltage, right? Say your handphone is 20%, you charge it up, then you will start from 20%, you will not start from 0. Here, of course, if your handphone's battery is fully flat, then you start from 0. Right? So this is quite easy to understand. When you have certain voltage initially there, right, you should put it in. Okay. So this equation is very important, right? You must remember, because from this equation, basically it gives you the second equation. Okay. You integrate it on both sides, and then you get the second one. And then the sign is determined by passive sign convention. Now, as I said, this important equations tells you all the properties of the capacitor. Okay, firstly, when the voltage changes over time, when there's a change in voltage over time, dV/dt, right? Change in voltage over time, the current is non-zero. Well, obviously, if dV/dt is not zero, your current is not zero. Now, the faster the changes of voltage, it means the larger value of dV/dt, the larger the current. In the extreme case where your dV/dt is, yes? What happened? Now, in the extreme case where dV/dt is infinite, basically it means you have a sharp change. It actually is quite easy to understand. You can just say that dV/dt is a small change in voltage over a change in time, right? Change in voltage over change in time. Now, this actually means that, for example, you increase from 0 to 5 volts within 0 time interval, right? So it's 5 divided by 0, which is infinite. Okay, if it's infinite, if dV/dt is infinite, your current is infinite, correct? Current is infinite, okay, which means that you can generate infinite current. Now, this is not possible. Okay, this means that you can easily generate energy, right, just by switching the voltage from one value to another. So this is not physically realizable. Because of these physical equations, we know that the voltage cannot change suddenly. And actually, it's quite easy to understand. You can't charge out your handphone battery immediately, right? When you charge out your handphone, let's assume this capacitor represents the handphone battery. You connect it to the power source, you switch it on, you put a resistor there to regulate the current, right? Control the value of the current. Once you switch it on, basically the voltage cannot immediately increase to Vs. It must gradually increase. All right? So this is what it means. The voltage across the capacitors cannot change suddenly. Right? It cannot change suddenly. You can just remember it this way. Your handphone cannot charge up immediately. Right? It must charge up slowly. Now this brings up an important property. Before switching, right, let's say you have 20% in your batteries, your handphone. Immediately after you switch on, it should start from 20%. You cannot start suddenly from 30%, or you cannot drop suddenly to 10%, right? It has to start at 20%, which is your initial storage. Okay, this basically is due to this property that I cannot have a sudden change in voltage, right? So the voltage must be changes gradually. So this is the first important property of the capacitor, right? And I don't even need to remember that. I just look at this equation and say that voltage cannot change suddenly, right? Because dV/dt is infinite. Then I know that it must be continuous, right? Immediately after switching. Okay, the next property is that when V is constant, DC is constant, isn't it, right? 5 volt constant. Okay, 10 volt constant, DC. Now, if it's constant, then there's no change of the voltage over time. So you go back to del V, del T. The voltage remain at 5 over time. It does not change. 0 with a change in time. Okay, which means that you get 0. Therefore, it just says that if a voltage is DC, right? If a voltage is DC, then dV/dt is equal to 0. Therefore, current will be equal to 0 because current is C dV/dt, right? So this equation gives you lots of information. And we know that if there's no current, this is like an open circuit. So capacitors basically acts like an open circuit. No current can flow through it to a DC voltage. And this happened at the steady state. Right? Suppose that you charge out a handphone, batteries again. Immediately after switching, you start from this initial storage. You did not charge it up from 0, correct? Maybe you start charging when they reach 20% because there's a warning. And then you start to increase slowly. You cannot change suddenly to the full voltage. Okay, but once it is fully charged up, you will remain constant, right? You will remain constant, and then your dV/dt is equal to 0. And steady state, usually we put t equal to infinity. Why? Because the infinity, surely it has reached steady state. So if you see infinity, it means steady state. We're referring to the steady state. Now, if dV/dt is equal to 0, then obviously your current will be equal to 0. Okay, this is also quite easy to understand. If you switch on, right, your power to charge up your battery, when it is fully charged up, right, when it's fully charged up, no current will flow into the battery anymore, correct? When it's fully charged up, right? You can view it this way. Initially, maybe this is 10 volts. And this one, if you charge from 20%, right, it will be 2 volts. Okay? So 10 volt minus 2 volts, 8 volt difference, so current will start flowing. This resistor is to regulate, right, the current flow through. Otherwise, you can see that the large current, right, will be flowing through these terminals. So this resistor is there to regulate, which is 8 volt divided by R. Now, once you start charging from 2 volts to 10 volts, your voltage will keep increasing. Now, when this reaches 10 volts, there's no potential difference anymore. All right, then your current will be equal to 0. So when it's fully charged up, then no current can flow through it anymore. So we say that it behaves like an open circuit. So to summarize, this equation is important. Memorize it, and from this equation, it gives you all the information that you need. Right? dV/dt, voltage cannot change suddenly. Otherwise, you have infinite current. Now, when V is constant, DC, then I is equal to 0. I equal to 0 means open circuits. Okay, so just one equations, you can deduce the two properties easily. So these two properties are important in analyzing a circuit with energy storage element, right? So please remember that. Okay, let's look at the first questions of this week tutorials. Yeah, you're given capacitors, right, with 4 mini F, and you're given the current, okay, and the initial voltage, right? Take note that initial voltage is given. So this means that your voltage is not charging up from 0 volts, right? It has an initial storage. Okay, this question you can see that is basically saying that given current, find V, right? Given current, find V. And also notice that the current over here is either positive or negative. So you should observe this, right? When current is positive, it's charging up. When it's negative, it's actually discharging. Just now we have seen this. When current is positive, it's charging up. This voltage is increasing. When current flow the other way around, it means that you switch it back to energy source, right? It is delivering energy. And these questions, we are given I, find voltage. This is current. You want to find voltage, so you should use this equation, right? Given I, find voltage, which means that you need to do integration, and you need to know the initial voltage. Okay, for the first part, the initial voltage is given. V0 is equal to 10 volts. So we start from 10 volts, then we start charging. And firstly, we have a positive current of 10 milliamperes. We charge out from 10 volts, right? Charge out from 10 volts. So we plug 10 milliamperes into here, and then we integrate it, divided by C. C is 4 times 10 to the power negative 3, right? Initial voltage is 10, so we add on the 10, and you integrate a constant, right? If you integrate a constant, you basically just get T. Integrate constants with respect to time, you get constant multiplied by T. Okay, this divided by this is 3.75. Okay, which means that our voltage, right? Our voltage during this period from 0 to 2, when your current is positive 50 milliamperes, is determined by this equation. Now it's a function of time, and this is a straight line equation, all right? Straight line equation, this is the gradient. So actually, if you plot it, this is how it looks like. Put t equal to 2. You put t equal to 2, that means the final time interval. You can check that it's actually equal to 17.5 volts. This means that when I put this current, which is a positive 50 milliamperes, my capacitor will charge up from 10 volts to 17.5 volts after 2 milliseconds, right? After 2 milliseconds. T is equal to 2 milliseconds. Now, next point is to note that my current suddenly switched from a positive 15 to negative 10. Okay, even though the current has suddenly switched from one value to another, I always remember that your voltage across a capacitor cannot change suddenly. Okay, which means that when your current switches to negative 10 milliamperes, this voltage has to start from 17.5. Right, then you will change according to the current that we have for the next time interval, which is negative 10 milliampere. Now, negative 10 means what? It will start discharging, correct? Current is now flowing the other way around, which means that it is now acting like a energy source. In this case, let's put this into here. Okay, and then we know that voltage cannot change suddenly. So it has to start from 17.5, right? Put 17.5 here, put negative 10 into here. Now you can see that integrating this, okay, you can get 2.5 T, right? This is 2.5 Well, integrating one with respect to time, you get t. And if you put t equal to 4, because the last time interval, right, is 4. We start from 2, end at 4. So if you put 4 into here, the voltage is equal to 12.5. Okay, which is lesser than this, correct? 17.5. Why? Because it's discharging. Negative current is discharging. So this capacitor is now discharging, and after another 2 milliseconds, the voltage dropped to 12.5 volts. So we have seen that when current is positive, it's charging up. When current is negative, it is discharging. Okay, the next part is that you have zero current. Zero current, right? Now positive current is charging, negative current discharging. How about zero current? No change, right? Zero current means no change. Voltage basically remain constant. Now, since voltage cannot change suddenly, right, we know that you will remain at 12.5 volts because immediately after switching is 12.5 and it does not change. So therefore, you will remain at 12.5. Right? If you understand that, you can just put 12.5 directly. If not, you can still get integrate, but integrate 0 is 0, right? 0 integration is the area under the curve. No area, 0. So you remain at 12.5. Okay, which means that I first charge it up and then I let it discharge. Okay, then there's nothing. I do not do anything, neither charging or discharging. So you remain at 12.5, right? Now for the last 2 milliseconds, the current switched to 10 milliampere. So you can do the same thing. Voltage cannot change suddenly, so you should start from 12.5, right? 12.5, and after switching, your current become 10 milliamperes, right? Put into this integrated from 4, right? Start from 4, and you can check that finally we get these equations. And if you put t equal to 8, you can check that the voltage is 17.5. So it's charging up again because it was 12.5 and it start charging up to 17.5 because your current is positive. So this is an overview. You are given this current over time, and then we use these integration equations, right, with the initial voltage of 10 given to you. Immediately after we put this current, right, my current cannot change suddenly, my voltage cannot change suddenly. It starts from V, and we have a positive current, so it's charging up. Now, after 2 milliseconds, you charge up to 17.5. Okay? And in between, right, you can use this equation to calculate the voltage. Now, after that, the current suddenly switched to negative value, but your voltage cannot change suddenly. So it starts from 17.5. Then it starts to discharge, right, because you have a negative current. Okay, after 2 milliseconds, it reaches 12.5. And then there's no current, so it remains constant for this time interval. And after that, we supply a positive current again, and then it starts charging up. So this is what we have done. Given current, find voltage. Now, you may want to go back and try, right? Do the reverse. Given voltage, right, just for exercise, find current. So this means that you differentiate. Okay, differentiate this. Okay, change in voltage over change in time, or you can differentiate all these equations. You'll see that you'll get back this one. So remember, given I find voltage, integrate. Voltage does not change suddenly, even if your current changes suddenly. Well, here, given voltage, find I, You differentiate voltage, multiply by C, right? And then you get the current. Any questions? Right, so please go back and try. Any questions for first part? If not, let us move on to the next questions. Okay, here we are given the circuits as in 3.2. And one thing to take note is that we are assuming DC conditions. Okay, actually this means that it has reached steady states, right? Reaches steady states. DC conditions. Just now we have seen that voltage cannot change suddenly, so it takes time to charge up. So we're assuming that, right, it has reached the steady state. This is called DC conditions. And remember that capacitor act like a open circuits, okay, under DC conditions, correct? Under DC conditions, because at steady states, no more change in voltage, right? It has fully charged up to the maximum voltage. Therefore, no change in voltage, even though there's a change in time. dV/dt equal to 0 means current is equal to 0. Current equal to 0 means open circuits, right? So usually you will denote this way. It means open because no current can flow through an open terminal, right? Okay, while short circuits means this, right? Voltage is equal to 0. Resistance is equal to 0, conductor. So given these circuits, under DC conditions, this two capacitor will be behaving like a open circuits, right? Will behave like an open circuits. Now look at these circuits. It's just a resistor network that we have learned in week 1 and week 2, okay, which means that treat it as resistor circuits, okay, because capacitor is now behave like an open terminals, and then analyze the circuits. Okay, what do you need to find? You want to find the voltage of the capacitor V1 and V2, right? What is the voltage across the two capacitors? Right, the voltages across the two capacitors V1, V2 at steady state, okay, which is this circuits over here. Okay, use any method as you wish, right? Any method as you wish. For example, if you want to use nodal analysis, this one will be V1, right? This one will be V1, and this will be V2. I take note that no current can flow through here. It's open. Now, if there's no current flowing through this 50 ohm resistor, what's the voltage drop? V is equal to IR, correct? V is equal to IR. 50 times 0 means 0 volts. Okay, therefore, basically, this is V2. Okay, I say again, if it's open, no current, no voltage. V is equal to IR. 0 amperes times 50 is 0, which means that this is V2. So after that, you just use nodal analysis. You can find V1 and V2, right? That's one way. Okay, any method is fine. So mesh analysis is also fine. Okay, for example, I just apply one mesh current, I. Because here, 0, right? No current, 0. So this one is known, the current is known. If you call this I1, I2 is equal to 0, in other words, which means that mesh analysis maybe is better. Only one equation. Just now I have two equations, right? V1, V2. So this one only one. You apply mesh analysis, go one round. You can write down these equations. Right? There's only one unknown I. Solve for it directly. Is 1 ampere. Okay, but of course, mesh analysis means find current. Nodal analysis find voltage. Okay, in the end, you still have to find this V1 and V2. But once you got a current, then current is related to voltage, correct? For example, this V1 is actually 30 times I. 30 times I. Why? Because if you look at this circuit again, these two are parallel. Right? These two are parallels. Okay, if you have the current, then you can get the voltage. So this is V1. Okay, if you are confused, then you just take KVL around this loop. Okay, this is I. Take KVL around this loop. You can also write down this equation. Then just put I equal to 1 into here. You can see that it is 30 volts. Okay, next, V2 is here. Now, just now I said that because there's no current flow through here, basically this is also your V2, right? This is also your V2, which is also, this means that this node voltage is V2. Now, if you look at this V2, V2 is actually 60. Now, this current I flow this way, all right? Go this way, so this is higher than this. Okay, it's higher than this, which means that you need to minus off. Any questions? All right, actually my current should be this way around, right? So if you define the other way, it's okay, you just get a negative answer. Any questions? Okay, we have seen how to simplify series combinations of resistors as well as parallel combinations of resistors. Actually, you can also do it for energy storage elements. Okay, but of course the property is different, and therefore, right, you simplify them in a different way. But here I'll just review what you have learned in your lectures. Okay, how do we combine, right, parallel combinations of capacitors? Now here we know that the circuit's law remain the same. Inflow is equal to outflow, Kirchhoff current law. The only difference is that I is now equal to C dV/dt, right? And we have C1, C2 to Cn, different capacitance, for example, but they have the same voltage because they are all parallel, right? All of them has the same voltage. Now this basically means that this dV/dt are the same because they have the same voltage. It means that you can take it out, right, from the common as a common term. The remaining part you can add them up, right, because all these are addition. Now if you look at this equation, it's equal to I is equal to C dV/dt. So this is the equivalent capacitance, right? Equivalent capacitance, which means that for parallel combinations you add them up. So it's the opposite of resistors, right? Resistors, if it's series, you add, but for capacitors, it is parallel, you add them up. Okay, as for series combinations, we add up the voltage, right? This voltage is applied across several capacitors, and for voltage is equal to integrations of I divided by capacitance plus initial voltage, right? Just now we have done this. So you have n capacitors, you just add them up all together. Now for series, remember current is the same current flow through all the capacitors. Right? The same current will flow through all the capacitors, which means that all these integrations are the same because capacitance are the same. And this means that I can take it out from the common term, and these are the total initial voltage, right, of the capacitors. So this is actually my equivalence, 1 over equivalent capacitance, and this is my equivalent initial voltage. Okay, I can treat it as if it's one capacitors. So for series, you can see that it is quite similar to the resistor in parallels. Remember, resistors in parallel, you do this, add up the conductance, correct? 1 over R1 plus 1 over R2, for example, right? Or you directly use this one, Req is equal to R1 R2 divided by R1 plus R2. So this actually means that CEQ, right, is C1 C2 divided by C1 plus C2. If you have only two capacitors, you can use this directly. Right? If you have more capacitors in parallels, the same as the resistors, it's better to use this. Right? 1 over C1 plus 1 over C2 plus 1 over Cn, then you invert it to get CEQ. Any questions? So to summarize, for series, you add up 1 over capacitance, right? 1 over capacitance, and then you invert it to get your equivalent capacitance. Or parallel is easier, just add them up directly. Okay, with this, we can now proceed to question 3. Now here you can see that you have circuits with many capacitors, all right? Many capacitors. Okay, you want to simplify it to one equivalent capacitance only. Right, so it is terminal A, terminal B. I want to simplify it to one equivalent capacitance. Right, so this is equivalent to this circuits with a certain equivalent capacitance. Okay, I will start by simplifying these two that I have circles or box up. So firstly, this is 80, this is 60, and they are parallel, right? Because they are connected to the same terminal on both sides, right? Or the same voltage basically applied across them, right? Same voltage. So same voltage means parallel. Now this three of them, these three capacitors are also parallel because one end they are all connected together. This is obvious. Now the other end, right? These two are obvious. They are connected together. Yeah, this is also considered connected together because these are conductor, right? No drop in voltage. So they are all connected together, which means that these three are also in parallel. Okay, remember parallel, you just add them up. Add them up. So this is simplified to 80 plus 40, right? This is 40, not 60. 80 plus 40 is 120. Well, this one, you can add up three of them together. Okay, therefore, it's 30, 30 plus 20 plus 10, which is equal to 60. Okay, which means that I add up, right? C1, C2, C3. I get the equivalent capacitance of 60. Okay, after that, we can see that these two are in series. All right, these two are in series because if there's a current flowing through here, the same current will flow through here. So they are in series, then we use this. Okay, but they have the same value, right? Same value. So as I said, same value is half. It means 60 times 60 divided by 60 plus 60. So it gives you half. So this is simplified to 30. Okay, after that, we can see that these two are in parallel because one end is common. Okay, the other end is also common, right? It's also common. This does not have any drop in voltage. It's a conductor. So same thing, we do this 150 times 30 divided by 50 plus 30. Sorry, these are parallel, so we add them up. 50 plus 30, right? Parallel is add up. 50 plus 30, we get 80. Okay, after that, these two are in series because the same current flow through them. Okay, in this case, we use this, or directly you use 80 times 120 divided by 80 plus 120, and you can check that it's 48. Okay, then these two are in parallel because they are connected to the same terminals on both ends, right? So we just add them up. 12 plus 48 give you 60. Lastly, these two are in series, same current, and therefore you multiply 60 by 12 divided by 60 plus 12, right? Or you use this one. 1 over CEQ is equal to 1 over C1 plus 1 over C2. And finally, you get 10. All this was in micro, right? That means 10 to the power of negative 6. So finally, we put 10 micro. Any questions? Okay, which means that we managed to simplify this complicated combinations of capacitors into one equivalent capacitance of 10 micro, right? So this is equivalent to a capacitor with a storage with a capacitance of 10 micro. Complicated combinations of capacitors into one equivalent capacitance of 10 micro, right? So this is equivalent to a capacitor with a storage with a capacitance of 10 micro. Any questions? Okay, we have seen the key properties of capacitors. Basically, as I say, I is equal to C dV dt, right? Based on this important equations, which you should remember, like you remember Ohm's law, you can easily write down two key properties. Voltage cannot change suddenly, and then capacitor behaves like an open circuit under DC conditions. Now, what about inductors, right? What about inductors? Now, inductors, again, it has these equations, which you should also remember, but however, you may actually see that it's quite easy to remember. Once you remember this one, okay, you just replace V by I by V, right? Just swap it around. Of course, you need to replace C by L, okay, which means that V is equal to L di dt. So you should also remember this, right? Equations. V is equal to L di dt, and from here, I can also deduce two properties. The current cannot change suddenly. Why? Di dt. If current change suddenly, di dt is infinity, you get infinite voltage, right? Which is not possible. Okay, next, under DC conditions, that means if I is constant, then there's no change of current over time, then voltage is zero. Now, if voltage is zero, then it behaves like a short circuit. So this behaves like an open circuit under DC conditions, while this inductor behaves like a short circuit under DC conditions. Okay, as I said, once you can write down these two equations, right, you can deduce this property very easily. Right? So firstly, current cannot change suddenly for inductor. Voltage cannot change suddenly for capacitors. And for capacitor, when voltage is constant, I is equal to 0. For inductor, when current is constant, voltage is equal to 0. Voltage equal to 0 means short circuit. Right? Short circuit basically means no resistance. Resistance equal to 0. It's a conductor, right, which you connect the 2 points. So similarly, V square L dt means what? Given current, find voltage. Given current, differentiate with respect to time, multiply by L, you get the voltage. Well, the reverse is integration, meaning that given voltage across the inductor, right? You integrate it divided by L, you need to add the initial current, and that will give you the current over time. Now, I will also briefly review, right, the formulas that you have learned in the lectures for the energy storage element. In particular, right, the energy of a capacitor, right, you should remember this is equal to half CV square, right, half CV square. Now, this is derived from the power, okay, because energy is the integrations of the power. Power is always V times I, right, as I explained to you, but the relationship between voltage and current may be different for different components. For resistors, V is equal to IR. For capacitor, I is equal to C dV dt, okay, which means that you should substitute I by C dV dt. Okay, then this is your power. Okay, if you integrate this power over time, okay, then here dt and dt cancel out, right? Which means that I'm integrating V with respect to voltage. Integrating V with respect to voltage gives you half V square. Half V square, and you're integrating from negative infinity to the current time. Now this basically means that let's assume that initially when this capacitor is made in the factory, right, of course there's no storage. If there's no storage, then there's no voltage. So the subsequent energy store will depend on this, right? CV square. Now, of course, if there's an initial storage, right, you just subtract it from the initial energy, then you get the change in energy. Right? So same thing for inductors. Right? You can follow this similar proof. V is equal to L di dt. I put into here dt cancel out. I'm integrating I with respect to I get half I squared, right? And assuming that there's initially no energy stored in the systems, then my energy is equal to L I squared. So these two equations you must remember. Okay, but you can see that it's also quite easy to remember. Just now I say that for this equation, you just replace V by I by V, C by L, right? So this is also the same CV square become Li square. Okay? CV square, Li square. So by remember one of them, actually you can just deduce the other one. Any questions? Any questions? No? Okay, next 3.4, question 3.4. Now it says that calculate the value of R. Now this question is actually the other way around, right? Usually you're given R, you try to find something, but this question says that design the resistors so that the energy stored in the capacitor, okay, will be the same as the energy stored in the inductor. Right, so this means what? Energy CV square is equal to Li square. So V is the voltage across this capacitor. Current I is the current flowing through the inductors, right? And we are given the capacitance as 160 micro. Our inductance is 4 mini H. Now this is the circuits givens, and remember that I is equal to C dV dt. So usually I'll just write down the equation so as to remind myself, and then V is equal to L di dt. Okay, at steady state means what? Voltage and current all constant. DC steady state, DC condition, voltage constant, then your current equal to 0, right? So no current can flow through here. This will become open. Now, at steady state, if your current is constant, then the voltage across the inductor will be equal to 0. This means that the circuits, right, basically is equivalent to this circuits over here under DC condition, because your capacitors is open, your inductors is short. And from this circuit you can see that it's just a resistor circuits. Okay, the only difference now is that we want to make the energy stored in these capacitors equal to the energy stored in the inductors at steady state, okay, by specifying this value of the resistor R. So firstly, the voltage across the capacitor is the voltage across the resistor, correct? In fact, if you look at this, these are parallel. These two are parallel. Okay, this means that VC, okay, is equal to current flowing through it. Now, if this is IL, because this is the current flowing through the inductor, and this is open, this is also IL, right? Because when the current flow through here, all flow downwards, none of them can flow through here. Current equal to 0 because it's open. Okay, therefore, we know that this voltage across the resistor is equal to IL times R. IL is the current flowing through the inductor, which is also the current flowing through the resistor. Okay, next, recall that the objective, right, is to design the value of R so as to make the energy stored in the capacitor equal to the energy stored in the inductor, which means what? Half CV square equal to LD equal to half L IL square. Now, IL is the current flowing through the inductor. VC is the voltage across the capacitor, right, when it's fully charged up, okay, in these circuits at DC steady state conditions. Okay, and we know that VC is equal to ILR square, correct? So you substitute this into these equations, this is what we get. And here we can see that current can cancel each other. IL square cancel IL square. Half cancel with half, which means that R square multiplied by C is equal to L. So R square is equal to L divided by C. C and L are given. You can check that this is equal to 25. right? Because it's R squared, so square root give you 5 ohms. Okay, this means that if you put this as 5 ohm, then it is possible to make the energy stored in both of the energy storage elements equal, right, at DC conditions. Any questions? Okay, you have seen that circuits with energy storage elements, under DC conditions, you can actually easily analyze it by treating the capacitor as open circuits and the inductor as closed, right? Closed circuits. Okay, and then basically you just analyze it as if they are resistor networks by using any methods that you learn in week 1 and week 2. So the methods that you learn in week 1 and 2 are very important. You use it over and over again, right? Even until the end of the course as well as your senior years, because these are the basic methods to analyze the electrical circuits. Okay, but however, we may also be interested in the transient. Now, transient means the stage between initially and steady state. Before it reached steady state, what happened? Just now I've shown you these circuits. Right? If you have a battery, you want to charge it up, initially 20%, and you charge it over time, it reach full, right? Full 100%. And because voltage cannot change suddenly, it will take time to charge up. Eventually, when you charge up, that's called steady state. Okay, before it reaches steady state, it's called transient. It's just a name to describe those things that are temporary, right? Not permanent. Steady state means no change. Okay? No change. Doesn't have to be constant. No change. If it's DC steady state, that means it's constant, right? If it's AC steady state, it means it's settled down as a sine wave, right? No more changes. Settle down as a sine wave. So initially, it may not be a sine wave, for example, but finally, it settled down as a sine wave. Okay? So steady state DC is easy to analyze, but something in between the transient is also important. For example, if you want to charge our handphone, you would like to know, right? How long would it take to charge it up? Okay, if you design something which take a few days to charge it up, then that's not good. So we want to know how long does it take to charge up? Okay, and then at any time, right? How much it can charge up? What is the percentage? If you charge on 20%, I want to know after 1 hour, right? What would be the percentage? After how many hours, right? You will fully charge up. So this is so-called the transient. And to analyze the transients, basically you will involve solving differential equation, right? Solving differential equation. So as I said, you need to review it. Okay, other than that, the circuit's laws still apply. For example, let's start from a source-free DC circuits, RC circuits. There's only one resistor and one capacitor, and there's no source. Now, when there's no source, right, please remember that there must be a initial storage. Okay, there must be an initial storage, otherwise there's no energy, meaning that the capacitor must have some energy. Then you'll start discharging, right? You'll start discharging, and you know that when it's fully discharged, the voltage will be 0, right? When you have charged up your battery, if you start using it, right? You connect to the load, you start using it. Eventually, of course, the voltage will reach 0, correct? Fully discharged, 0%. So that's easy to understand. Initially, maybe you have a voltage. At steady state, it will be 0 volts. Okay, what we want to know is what happened in between. Right? Steady state we know. Initial we know because voltage cannot change suddenly. Immediately after switching, right, after you start discharging, it must start from this, but how about those voltages in between before it reaches steady state, starting from this initial voltage. So this is called transient, and you need to analyze it by circuit analysis. Now, circuit's laws still apply, right? For example, KCL, if this is IC, this is IRL, or specifying passive sign convention, all right? High to low, right? High to low. So I is equal to C dV/dt for current flowing through the capacitors. For resistors is V over R. And both, right? I'm using passive sign convention. Flow from high to low. Okay, the only difference is that now, because of this dV/dt, you ended up with a differential equation. And this is called a first order differential equation because you only differentiate it once, dV/dt. If you differentiate twice, if your equation involves d squared v dt squared, then it's called second order, right? If you have d cubed v dt cubed, it's called third order. So this is first order differential equations. Then you come to the next part, right? How to solve this first order differential equation. Okay, for linear equation, you can easily solve it. One equation, one unknown, you just solve it directly by algebraic manipulation. But unfortunately, differential equations, dV/dt is not equal to V, right? dV/dt is the change of V over time. This means that you need to know the max part. Okay, here I'll briefly review it. Okay, what we want to know is that how this voltage will change over time. I want to get voltage as a function of the time from this equation. How your voltage will change over time by solving this differential equation. But we know that finally it will be zero because you have a battery, you use it for a long time, right? At steady state, it will be zero. Now, how about those in between? Okay, and to do that, you need to solve this differential equation. Okay, another way to look at this differential equation is that dV/dt is equal to negative AV. Just move this to the other side of the equation. It means that you need to find something that even after you differentiate it, it is still in the form of V, right? Even after you differentiate it, it's still in the form of V, okay, and it's negative, and it has a constant. So it's kind of dV/dt is proportional to V. And actually this should remind you of this exponential term, because we know that if you differentiate this exponential term, it's still in the same form. In fact, if V is K, a constant multiplied by EST, another constant S, then dV/dt, you just bring S to the front, which means that, right, it is still proportional to your V, correct? Still proportional to your V. So over here, dV/dt is equal to SK EST. Okay, you put it into this differential equations, right? This whole thing put into here, this is what you get. And V is equal to K EST. Put it into here, you get A multiplied by V, right? So this is my V, and this is my dV/dt. Now this common term can take out. You remember right hand side equal to 0, equate to 0. Exponential term cannot be 0. You will reach it close to 0, but can never be 0. K is not equal to 0, otherwise there's no solution, right? V is equal to 0. Therefore, the only thing is possible is S plus A is equal to 0, okay, which means that S is equal to negative A. Right? This is easy to understand because we want something, right, which is negative. We want to have something which is negative, so the answer is this one, right? If you differentiate this one, you get a negative A at the front, right? This is what we want, a negative A at the front. And finally, right, K is the initial voltage. Why? Because if you look at this equation, V is equal to K is the unknown. Okay, we want something which is e to the power of negative at, so that when you differentiate with respect to time, you get negative a, right, to the front. This is what we want over here. Multiplied by v. Okay, but what about k? Now, k is actually the initial voltage. Why? Because when you put t equal to 0, then Vt t equal to 0 is V at t equal to 0 is equal to k multiplied by e to the power of 0, t equal to 0. E to the power of 0 is 1. So k is your initial voltage, right? K is your initial voltage. That means that the solutions of this differential equations is simply Vt equal to the initial voltage e to the power of negative at. And what is a? Notice that a is this term over here, correct? If you go back to this, this is your a, 1 over RC. Okay? 1 over RC, okay, which means that this is dVdt plus AV. A is equal to 1 over RC. So my solutions is basically V0 e to the power 1 over RC t. So this is the solutions of the differential equation. Okay, from there, then we know that it reduces exponentially. All right, exponentially. Now this equations, right, if you check Vt is equal to V0 initial voltage. This is my V0 e to the power of negative 1 over RC, your A, multiplied by t. Now, t equal to 0, you're here. T equal to infinity, steady state, 0, correct? V goes to 0. In between any time, you can calculate the voltage. So that's called the transient. Before it reaches steady states, at any time instance, I want to know the voltage. Okay, the next question is that no need, we want to know the voltage. We want to know how fast, correct? Some could be faster to reach steady state. Some could take a longer time to reach steady state, right? As I said, if you want to design something to charge up or discharge, right? Charging up, you want to be fast, right? But discharging, you may want to be slow. So this is a different circuitry altogether. Over here, we are looking at the discharging part of this simple source-free circuits. And if you want to know how fast you charge and discharge, there's a concept we call time constant, okay, which is simply RC. Okay, this is basically derived by setting your T equal to RC. Okay, if you put T equal to RC, which we call the time constant, tau, then what will happen is that your voltage will be V0 e to the power of negative 1, right? E to the power of negative 1. So remember this. E to the power of negative 1 is 1 over E. And E basically is constants, okay, exponential terms. And you can check that is equal, 1 over E is basically equal to 0.368, right? 0.368. This basically means that this is 0.368. Now, it basically means that when T is equal to RC, your time constant, right, then your voltage, okay, will reach this value, which is 36.8% of your initial value. If the initial value is here, then you'll reach 36.8% of your initial voltage when T is equal to tau. So this is the indications of how fast your voltage is discharging. And you can see that the larger the time constant, the longer time it takes to discharge. The shorter the time constant, the faster it takes to discharge to 36.8% of the initial voltage. Any questions? Okay, next is that why do we put this tau equal to RC? Well, it's just for convenience, because if tau is equal to RC, then if time is equal to RC, then basically we have 1, correct? Because this at this time, RC, then you have 1. And e to the power -1 is a fixed constant, 36.8%. Okay, basically you are just setting a reference and see, right, how fast they take to reach this reference. You can't do it at a steady state, because you can see that the steady state is something which is not possible to measure. Now, how about 50%? Right, 50% you can, but you need more work to calculate. Well, for this case, RC is very easy to calculate, right? And we know that the standard is that it reached 36.8%. So remember, time constant is the time taken for your voltage to discharge, right, to reach 36.8% of the initial voltage. And that gives you indications of how fast it takes for this source-free RC circuits to discharge. Now, this is an example in your lecture notes, because you have seen RC circuits, correct? RC circuits, which is a source-free RC circuits. Okay, but we know that circuits in general is not just RC circuits. You have, for example, right, many resistors with one capacitors. Okay, but remember, we have learned many methods to simplify circuits in week 1 and week 2. So the key idea is that if you have a more complex circuits, then simplify it to the equivalent circuits by using what you have learned in week 1 and week 2. So in energy storage element, you will notice that it's stuck with some equivalent circuit actually. Okay, that means that imagine you have some complex circuits such as this one. Then you have managed to simplify it to this, okay, with only one resistors. Then from here, I start analyzing it. And fortunately, right, you need not remember all this max. Okay, but I suggest that you read through it once, understand how it works. Okay, after that, what you need to do is to know that the solution take this form. Okay, the solution take this form. So the whole idea of this circuit analysis or this energy storage element is that if you have a complex circuits, simplify it to the equivalent one, right? Then from there, you know the solution take this form, correct? The solution take this form, okay, which means that you need to calculate a few things. What is the time constant? Okay, what is the initial voltage? If the initial voltage is given, then just use it. If it's not given, in some cases there's a switch, right? Switch from one instant to another. You need to calculate the initial voltage before switching. And voltage cannot change suddenly, then it will become the voltage after switching, right? So the whole idea is that. And what about your resistors? You just convert it into Req. Then time constant is Req multiplied by C. You then put this 1 over tau, right? 1 over tau into here. You get this solutions, initial voltage 45. So you can get this particular solutions, which is how your voltage will change over time, right? How your voltage across the capacitor will change over time. Any questions? So same thing for your second order system. You may notice that you will start from some standard circuits. And that is actually assuming that you have already simplified it, right? Simplify it to the equivalent form. So the whole idea works this way, right? As I said, some complex circuits simplified to the equivalent form, and from the equivalent form, you know that the solutions, right? Solutions will take this form: initial voltage e to the power of negative t divided by RC. R become Req. C is this value over here, okay, which means that I can go straight, right, from here to here. Circuit analysis. Here is the solutions of the first order differential equation. So the problems reduces to find V0 and find Req, right? So I hope that everybody can see that it's not so much about all this max actually. Okay, the max part, you just need to read through it once, right? Do not ignore it. Read through it once, knowing that this gives you this, right? Otherwise, you will be wondering, how do I get this? Right? This is from max solving a differential equation. But in solving circuits problems, we can go straight to this, saying that, okay, because it has transformed to this RC circuits, and we know that this represents these differential equations, and the solution is this. This means that I will just find my Req, right? Find my initial voltage, and then I do my solution. So this you will deal with it in the next week tutorial. Okay, here we have a related problems, but not exactly the same, because in here you have already given your current and voltages. Usually we want to find, but here you are already given. Okay, you work backwards to calculate RC. Right? Usually it's the other way around. Given RC, find, right? Find voltage and current, but this is the reverse. Okay, given voltage and current, we want to find certain parameters of the circuits. So for example, maybe you go to the lab, you use some instruments to measure, right, all this, and then maybe you want to work backwards to calculate what will be the equivalent resistance, okay, what will be your capacitance, and what will be the time constant, how fast. And notice that there's also a question asking you to find the time required for the voltage to decay to half. Now, just now I mentioned, right, why not half? Why 36.8%? Because 36.8% is easy. Time constant is R times C. Finish. Right? If you want to find half, then there's additional work. Later on we will see. So 36.8 is just a standard. Right? Imagine that you have a race. We say 100 meters. So 100 meters, how fast people can run? That is the standard based on 100 meters. So same thing, 36.8 is just a standard that we set to see how fast you will reach that, right, value, 36.8 of the initial voltage. Okay, for this question is the reverse. You have already given your voltage and current. Okay, remember what is time constant? Is the time taken for it to reach e to the power of negative 1. Okay, which means that if you put this over here, 2e to the power 200t, right? 200t. So when this is equal to 1, it means what? 200t is equal to 1. So t is equal to 1 over 200. We call this the time constant. Usually we use this notation tau, right? Tau. So tau is equal to 1 over 200. Okay, which means that if you put t equal to 5 milliseconds into here, then this will become e to the power of negative 1, which means that you reach 36.8% of the initial voltage, which is 56 in this case. So remember, you just put this, right, 200t equal to 1. Then you have e to the power of -1. That t is called the time constant. In this case, it's 5 milliseconds. Okay, next is to note that for the resistor, V is equal to IRL. All right, V is equal to IRL for this resistors, and V and I are given. Over here, we substitute into the Ohm's law. V is equal to I times RL. Exponential term can cancel out. This gives you the resistance. It's equal to 7 kilo ohms. Right, so as I said, we work backwards. Given the current and voltages, maybe through measurements, we want to work backwards to calculate the equivalent resistance, right, of these circuits. Now, you have now obtained RL, correct? You have now obtained RLs. Let's go back to these circuits. We have now obtained the time constants. We have now obtained RL. We want to find C. Time constant is RC. So once you know the R, once you know the time constants, obviously you can calculate C. C is equal to tau divided by R, right? Tau divided by R. Tau is 1 over 200, or you use 5 milliseconds, 5 times 10 to the power -3 divided by R, right? You can get the same answer, which is 0.7143 times 10 to the power -6. Okay, we have seen that time constant is 5 milliseconds, which is the time taken to reach 36.8% of the initial voltage, right? 36.8% of 56. Okay, the next question says that you want to find the time taken to reach half, right? So this is another standard which is not as straightforward to calculate as the time constant. Time constant, you can see there, I just do this, set 200t equal to 1, then time constant is 1 over 200. Okay, if you want to use 50% as a standard, you can see that it's not that straightforward. Okay, in this case, what we will do is that half means half of the initial value. Initial value 56, half of it, right, give you 28. Then you find the time for the voltage to reach 28, right? Then you need to solve these equations. Okay, this is half, right? So this cancel out. It means e to the power of negative 200t is half. So e to the power of 200t is 2. Taking ln on both sides, you get 200t equal to ln 2. Then t is equal to ln 2 divided by 200. So this involves a few steps. Okay, and it's not as straightforward as your RC, right? Just multiply R by C. And ultimately what we want to know is that how fast, right? Which one is faster? So therefore time constants, remember, is just a standard which is convenient to see which of the circuits, right, discharge at a faster time. Any questions? Okay, so we have started energy storage elements and circuit analysis of energy storage element. So I hope everybody can get the idea from this tutorials. Right, you have a complex circuits with energy storage element. So the whole idea is that you want to convert it to some equivalent circuits. Okay, in a certain standard form. Then you get the solution directly, right? You go straight to the solutions. For the first order circuits, just now we shown that is e to the power of negative t divided by RC. Right? So the R is your equivalent resistance. If you have a complex circuits, there is your equivalent resistance, and this is for source free, right? For source free. Now, if you have a source, then you have a different solution. So your equivalent circuits will be different. Right? You have different solutions, and for second order, you also have different solutions. So what you will see in your lecture is that you will start with all these equivalent circuits. It can be first order equivalent, second order equivalent, by assuming that we have already do the simplification, right? Already do the simplifications based on what we have learned in week 1 and week 2. For example, you can transform circuits into the equivalent circuits by using Thevenin's equivalent, right? You can also use source transformation to simplify the circuits into its equivalent form. Then after that, you just take out the solutions. Okay, and for this course, actually you're not expected to solve it by presenting the solutions of the differential equations. What you need to do is to understand, right, how it was done, okay, at least one time, okay, because it's meaningless to memorize some equation if you don't even know, right, how it was derived. What is important is that you need not remember, right, how it was derived, but you read through it with the objective of understanding how it was derived. Okay, after that, what you need to do is to use all these solutions directly. Okay, of course, this may involve some memorizing of these solutions. Okay, but when we go to the Laplace transformations, right, you'll see that, right, later on I'll point out to you, you'll see that all these are actually in the Laplace transformation table, right, which is given to you. So in fact, if you understand the link, you can actually try to see it from the Laplace transformation table as well. Right? But at this stage, what you need to do is to understand that different equivalent circuits, right, give you different solutions. Okay? For example, later on you may have series RLC, parallel RLC. Will give you different solutions. You need to know how to determine the solutions, right, based on the equivalent circuits. Okay, for more complex circuits, what you need to do is to use circuit analysis, week 1, week 2, transform it to this equivalent form, or you can view it as a standard form, that you can get the solution, right? So remember, complex circuits transform, simplify to equivalent form so as to link up with the solutions that we have derived, right, in the lectures. And the energy storage elements problems, right, basically circuit analysis of the energy storage, circuits with energy storage, would basically involve all these simplifications as well as to link up with the solutions of the equivalent circuits. Okay, we'll see that in more details, but I suggest that you go back, right? Try to read through your notes again, then you understand why. So basically, your notes start with this. Knowing the solutions, derive the solutions in this form. And from there onwards, any other circuits, we just transform to this form and then link up with the solution. Any questions? Okay, if not, I'll stop here today. Thank you.